Hello friends, hope you are doing well. I have few questions for you. Can we use copper K alpha to find the crystal structure of iron? And K alpha, K beta, K absorption rate. Out of these three, which one is having maximum energy and how? And we know the filter atomic number is usually less than one or two atomic numbers less than the target metal. Why is this so? When we hit the target metal with electrons, we'll get the X-ray profile like this. But most of the characterization techniques demand monochromatic wavelength. We try to reduce the relative intensities of K beta and K alpha. So when we produce X-rays, they go through filter in turn giving almost monochromatic wavelength. Before looking at the how filter works, let's look at what is K absorption edge. Friends, we know there are different shell inside an atom. This is nucleus, K shell, L shell and M shell. So K shell is the closest to the nucleus and L shell and then M shell. So binding energy of K shell is maximum out of these three. So for better understanding, let's give some numbers. So binding energy of K shell, let's say is 100. L is little away from nucleus, so let's consider it as 80. And for M shell, this is 60. So this is the binding energy of that electron inside an atom. We know K alpha, K beta, these occur when there is a jump in electron from these shells, right? So for K alpha, we need to, there is an electron jump from L shell to K shell. So the K alpha is nothing but, the energy of K alpha is nothing but the energy difference between these two shells. So K alpha is nothing but 100 minus 80 is 20, right? For K beta, we know it should be from M shell to K shell. So here also K beta is nothing but 100 minus 60. So this is 40. So the energy of K beta is greater than K alpha. Now, if you look at the K absorption edge, it is nothing but the energy required to knock off an electron from K shell. So here, the energy of the K edge is nothing but the binding energy of electron in the K shell, which is nothing but K edge is having energy of 100. We understand that for the same metal, K absorption edge is greater than, K beta is greater than, K alpha is, this is nothing but energy. The main purpose of filter is to absorb the unwanted wavelengths. Friends, if a wavelength is extremely high, which means its energy is low, so that gets easily absorbed. So with increasing the energy or the decreasing the wavelength of an X-ray, the absorptivity decreases and penetration increases. So higher the energy, penetration is more and the absorption is less. So if we plot the intensity that gets absorbed or mass absorption coefficient with respect to lambda, with the decreasing lambda, which is nothing but increasing the energy, the absorptivity gradually decreases, right? But at a certain energy, it suddenly increases, and after that it again falls. This sharp increase at certain lambda is called K edge, and it is because of this energy is sufficient to knock off an electron from the K shell. So this sharp rise, this all the energy that is absorbed is being utilized to knock off the electron. So this is called K edge. Friends, we just understood that the energies are like this for a single metal. K alpha is having lower energy and then K beta, and K edge is having even higher energy than these two. And we understand to decrease the unwanted wavelengths, our filter should be in between these two. If our K absorption edge is greater than K alpha but less than K beta, which means the energy required to knock off electron is this, and K beta is having more energy than that. So all these energies are consumed to knock off an electron and this intensity gets absorbed. But K alpha does not get affected. Why? Because this energy is insufficient to knock off an electron from the K shell. Since K edge of that particular metal is greater than K beta, we cannot use, for example, if copper is our target, we cannot use copper as a filter for that. We are going to choose a filter which is having K absorption edge between K alpha and K beta. So we are going to choose filter whose profile is like this, which means the energies which are greater than this, which means K beta and all, these all are going to get absorbed, and in the end we are going to left with almost K alpha. So after using the filter, intensity of K beta is extremely reduced and the relative intensity of K alpha is very high, which is what we want for our experimental purposes. With increasing atomic number, binding energy of K shell electron increases. Why? Because there are more protons and neutrons in the nucleus, so binding energy increases. We understand that for the same metal, K absorption edge is greater than K beta and K alpha. Now, our choice of filter, K edge should fall between these two, which is nothing but the binding energy should be less for the filter. So if we reduce the atomic number, binding energy decreases. So this is wavelength scale. So if by decreasing one or two atomic numbers, the K edge falls between K beta and K alpha. So that is the reason we choose the filter which is having one or two atomic numbers less than the target. This is target, this is filter. So filter is having K absorption edge lower than the K absorption edge of the target metal, so that it falls in between K beta and K alpha and it takes care of the extra unwanted wavelengths. When we are going for the diffraction of a polycrystalline material, we require single wavelength. And I would like you to comment in the comment section, what is the technique which uses this wide radiation, mixed wavelengths, to find the crystal structure of a single crystal? So for a polycrystalline material, we use this. For a single crystal, there is a method which uses the mixed wavelengths. Please do comment that method. Friends, if we look at copper K alpha, which is nothing but 1.54 angstroms, its wavelength. If you look at iron K absorption, it is 1.53 angstroms, which is nothing but wavelength greater than that of copper K alpha. We learned that the filter should have a wavelength in between K alpha and K beta so that it will absorb K beta. But if you look at iron, which is having K absorption edge, right? This is 1.54, this must be 1.73. So it is having K absorption edge here. So it is nothing but, it goes like this. So we want K alpha, but iron is absorbing all the K alpha and K beta. So if what happens if we use copper K alpha to find the crystal structure of iron, almost all the intensity is absorbed in the iron. So there is no diffracted wave which will give us the peaks in the XRD profile. So the conclusion is we cannot use copper K alpha for iron as the energy of K absorption edge is lower than the K alpha. Friends, now we have answers to all the three questions that I mentioned earlier. Can we use copper K alpha for iron X-ray diffraction? No, we cannot use. And we know the energy of K edge is greater than K beta is greater than K alpha, and this is the main principle behind the filter selection. And we understood that filter should have an atomic number 1 or 2 less than target so that it falls in between K alpha and K beta. Now there is a question for you. Why do we have K alpha doublet? We know that there is K alpha 1 and K alpha 2 in the X-ray profile after generation. So I would like you to find the answer to this. Why only 2? Why not K alpha 3 or K alpha 4? Why do we have exactly 2? And what is the reason behind this? Please drop a comment on this question if you know the answer. Thank you so much for watching, friends. If you want me to make more of such videos, please drop a comment. I'll keep doing more of such interesting videos. Take care. See you in the next video.